Today we're going to talk a little bit about nuclear energy. There are two major nuclear processes, fission and fusion. Fission is the process where nuclei split. When you have a fissure in a rock, it's a split in the rock. So that's the term that means to split the atom. And it produces large amounts of energy. And many of the larger elements above, some of the isotopes above mercury and all of the isotopes above thorium can be made to undergo fission. And this is just a sample of a type of nuclear fission process where you take uranium, you bombard the uranium nucleus with neutrons, and when it does, it splits it into two smaller isotopes of krypton and barium, gives off extra neutrons and lots of energy. And those neutrons then, if you think about that, as those neutrons are produced, they can in turn strike other nuclei, which will produce three more neutrons, which can strike even more nuclei. So you get this chain reaction that occurs, and that chain reaction can result in an explosion. And if it does explode, you see that classic mushroom cloud that we see on TV when they show a nuclear explosion. Now, the amount of material you need to keep a nuclear reaction going is called the critical mass. If you don't have enough mass together, then the neutrons are going to escape before they can ever set up any kind of a chain reaction. If you have a controlled fission reaction, that's a nuclear reactor, and here close to us is Comanche Peak. If you have an uncontrolled fission reaction, that's your atomic bomb. So that's just a little introduction into fission. Now, fusion, on the other hand, is a process that occurs in the sun. Fusion takes two small elements, in this case, two isotopes of hydrogen, tritium and deuterium, both of which have neutrons in the nucleus, unlike normal hydrogen, which just has one proton. But when they fuse together, they form a helium isotope, and they give off a neutron, and again, tons and tons and tons of energy. And that's depicted in the drawing below. As I said before, fusion is the power of the sun. If you have an uncontrolled fusion reaction, you get a hydrogen bomb. And a hydrogen bomb is hugely powerful. It takes large amounts of energy, high temperatures to start that fusion reaction, which means they use an atomic bomb just to detonate the fusion reaction. A controlled nuclear fusion situation, we have done it, but getting it cheap enough to be practical is the issue. It still needs those high temperatures, so it requires a lot of energy input to get it started. So if your output isn't much more than your input, or if it's not even as much as your input, then it's not going to be an efficient way to get energy. As it says here, one of the primary difficulties in using nuclear energy is the disposal of the waste, which is often highly radioactive and often even more dangerous than the fuel they used in the first place. The half-life of a radioactive isotope is one of the ways that we use to indicate how dangerous that particular isotope is going to be to the environment. Half-life is the amount of time it requires for half of a radioactive sample to decay. That's the half-life. Now keep in mind, when we say decay, the sample doesn't disappear, it just changes into a different isotope. Eventually, it keeps going with that nuclear process until it reaches an isotope that's stable and not radioactive. And again, this is going to give us an idea of how long that radioactive isotope or that radioisotope is going to stick around. So, an example, iridium-182 has a half-life of 15 minutes. How much of a 40-gram sample will remain after 1 hour? So, this is our half-life, often represented by a small t sub 1/2 of 15 minutes. We're starting out with a 40-gram sample. So that's going to be our mass at t equals 0, time equals 0, What's the amount we have to start with? After 15 minutes, half of that is going to decay. It's going to turn into something else. But our point is we only have 20 grams of that sample left after 15 minutes. After 30 minutes, half of this is going to decay, so we'll be left with 10 grams. After another 15 minutes, a total of 45 minutes, we're only going to have 5 grams left. And finally, after 60 minutes, which is our 1 hour, we're going to have half of that, which is 2.5 grams. So that's how we calculate a problem that has an even half-life passing. Now, there's a more difficult type of problem that we do in AP that involves kind of a different kind of an equation to do it. But for these ones that have even half-lives and even times that have elapsed, this is the way that we're going to do it this year. So, final example. Tritium, which is the isotope of hydrogen that has 1 proton and 2 neutrons, has a half-life of about 12 years. So the half-life is 12 years. If you started with 20 grams of tritium, how much would you have in 48 years? So let's start out. Remember, we want our mass at T equals 0. And at the very beginning, our mass is 20 grams of our tritium. Now we're going to go 1 half-life at a time until we reach our total time elapsed. So this is our time elapsed. So if we have 12 years then, for our first half-life, we're going to be down to 10 grams. Another 12 years, which is going to be 24 years, we're going to be down to 5 grams. Another 12 years, now we're up to 36 years, we're going to be down to 2.5 grams. And finally, after another 12 years, we've reached our time elapsed here of 48 years. We're going to have 1.25 grams. And that's our answer.